Welcome to section 3 of chapter 4, everyone. We will be learning about a shortcut to show if triangles are congruent. But before that, I was trying to make a ping pong cannon earlier to show a few things in science, and it wasn't working. I think it's because of the vacuum. It really sucks. Well, I guess it doesn't suck. Either way, moving on. We're going to be in section 3 for today. The first concept is a pretty straightforward one. We just want to learn about how to make a flow proof. This is actually something that your book goes into in section 5. However, I want to take care of it right now. It uses a flow chart to show reasons and statements of proofs. Main reason is so that way it shows cause and effect. These statements cause these statements, which cause these statements, and they're all connected by arrows with the reason that we can say them underneath. An example would be like this. Over here on the left side, these would usually be the first two statements. They're usually a given or something I pull from the diagram. The next ones over here, these ones are the effect of these ones being true. So there's arrows leading to them, so these two statements actually combine to make this one here. I realize that there isn't an actual proof here yet, but these over here on this side, these are the statements. These are the effect of the statement before it. So for instance, statement 1 and statement 2 calls statement 3. Statement 3 calls statement 4. And this is an example of what a flow proof would look like. They can go left to right. They can go up, down, left, right, right, left, down, up. They've just got to show the arrows and the sequence so that way people know how to follow it. This example was actually one from last section, so you don't have to recopy it down. It should already be in your notes. It was example 6, I believe, in section 3 of chapter 3. But this was a proof that we had before. Given, copied down there. Then we said angle 3 and angle 2 were congruent because of the vertical angles congruence theorem. We said, hey, these two combined to make this statement here. Transitive property. And last but not least, we said, hey, if these two are congruent, then the two lines are parallel. Corresponding angles, converse postulate. Well, how would that look like in a flow proof? This is how. These two statements I either got from the diagram or they were given to me. So let's look back here. I pulled angle 2 and angle 3 being vertical angles. Yep, I didn't get that from the statement before it. I looked at the diagram, got it. Angle 1 being congruent to angle 2, that's something I was given. So if I look here, those two are the first two here, and there's nothing before them because there's no statement that causes them. I either saw in the diagram or it was given to me. The next one, angle 3 being congruent to angle 1, it's a combination of these two. Angle 1 is congruent to angle 2, and angle 3 is congruent to angle 2. And because they're congruent to the same angle 1 and angle 3 have to be congruent to each other. That happens to be the transitive property. And these two statements combine for this one. And then last but not least, if this is true, angle 1 and angle 3 being congruent, that calls the lines to be parallel. So this is a direct link right there. There's one arrow. Good. Done. And there we go. That's an example of a flow proof. It's up to you if you want to do 2-column like up here, or flow proof, unless I specifically ask for one or the other. Personally, now that you have the option of flow proof, I would probably be using that. Alright, the next concept is the shortcut I'm trying to teach you. If you take 3 lengths, it doesn't matter what 3 lengths. For instance, if I took 2, why am I drawing a blank on their name? 2 popsicles. 2 popsicle sticks and a pen. If I tried to arrange these end to end, there's only one way I could do it, like such. It doesn't matter how I would rearrange these pieces. They would still make the same shape. In fact, the exact same shape. As long as I know 3 sides in one triangle are congruent to 3 corresponding sides in another triangle, I know those 2 triangles have to be congruent in some way, shape, or form. So in this instance here, we saw this earlier in this chapter, If I had segment MN congruent to segment QR, segment MP congruent to segment QS, and segment NP congruent to RS, there's no way around it. Those two triangles have to be congruent. I don't even need to know anything about their angles to say, hey, those two are congruent. So those corresponding sides being congruent causes the triangles to be congruent. That's what the side-side-side congruence postulate says. It's also another thing, if you look, it's a postulate. No matter what I do, I can't prove it to you. However, I can try and convince you by showing and demonstrating it as much as possible, but I can't actually prove it. You're going to have to accept this one, or ask me to show a whole bunch of different examples of it, and hopefully it'll click. Alright, let's look at an example. This is the second example today. What if they ask me to prove that two triangles are congruent? Alright, so they tell me the given. C is the midpoint of segment AE and segment BD. Segment AB is congruent to segment DE. And they want me to prove that triangle ABC is congruent to triangle EDC. Alright, I want you to try this one on your own. I'm going to be doing it in a form of foolproof. So the first thing I do is I copy down the given. And I put them into two bubbles, one on top into the other. And that's where I'm at. And now from here, do your best to try and figure out what causes what here. Alright, if I look at this, I can't think of any way to go from this one here. Alright, this segment and this segment are congruent. Whoop-de-doo. Now, I might know something about vertical angles here, like angle DCE and angle ACB. However, if I'm trying to do the side-side-side congruence postulate, I'm going to want to get the sides to be congruent. So if I could somehow show that segment AC and segment CE, again in this congruence thing, they're the last and the first letter, so those two have to be congruent. If I could somehow say those two are congruent, that would sure help. Same thing with segment BC and segment CD. If I could somehow say they're congruent, awesome. If I look, I know that C is the midpoint. Hold up. A midpoint cuts a segment into two congruent segments. So if C is the midpoint, that means it cuts segment AE into two congruent segments, segment AC and segment CE. And consequently, the same is also true for segment BC and segment CD. These two are congruent and these two are congruent because that's what it means for C to be a midpoint. If it's a midpoint, it cuts it into two congruent segments. So if I look now, I have a side, and a side. Side, side, side. Three sides. I now can say the triangles are congruent. And because I'm using three sides, it's side, side, side congruence postulate. And you see how these arrows are drawn? This big one here causes both of these smaller ones because of the definition of midpoint. Then this one, and this one in combination all combine to say that the triangles are congruent. There we go. Example 3. Is triangle ABC congruent to triangle DEF? In this one, what they're doing is they're just going to give us a few coordinates. And they want us to show that those triangles are potentially congruent. What's your thought about how to try and show that triangle ABC is congruent to triangle DEF? Alright, if you said, I think that we're going to have to use the distance formula and check to see if segment AB is equal to segment DE. Again, first two letters, first two letters. Length of segment BC is equal to length of segment EF, last two letters, last two letters. And length of segment AC is equal to length of segment DF, first and last, first and last. So if the distance formula says that is true, then I think I've got two congruent triangles because of side, side, side. So if yes, then triangles are congruent. If no, then the triangles are not congruent. At this point, I'm going to do the distance formula for AC and DF on the board behind me. I'm not going to say a whole lot about them. However, they will be written out here. Sorry, I'll be doing the distance formula for segment BC and segment EF. Those are the ones that'll be a little bit tougher. Okay. All right. For B, the coordinates were 4, 4. And for C, it was 1, -1. That's where I got the coordinates from. Now it's time to plug it in. All right, so I got length of segment BC to be square root of 34. I could try and make it easier. However, if it is equal to length of segment EF, I will get the same exact number, so there's no point in reducing it. All right, so the coordinate for E was -5, -2. And then the coordinate for F was -2, 3. That's where I got the coordinates. Now it's time to just plug it in and solve. All right, and I got EF to also be the square root of 34. Good, matches up. This and those two are equal in measure. So now all I have to do is check AB and DE and AC and DF. So I look, square root of 34 equals square root of 34. 3 equals 3. 5 equals 5. Last but not least, I would say these two triangles have to be congruent by the side-side-side congruence postulate. If I don't say it, I've got a whole lot of work, but my conclusion is lacking. It doesn't carry the meat of the work. And those are the two main types of things that I'll ask you to do. Yeah, I might ask you to look at a triangle and say, hey, are these congruent? You're going to have to look for information like reflexive property, something that's not marked, but it's the same segment for both triangles. Something like, hey, that's a midpoint, so that's actually two congruent segments. Oh, that's a bisector. It cuts it into two congruent segments. Cool. You're going to have to use some of these ones that deal with segments a bit to your advantage to be able to do these problems. All right, there's one last thing that we need to make sure that we have here, and that's stable shapes. If I think of the side-side-side congruence postulate, it says if I have three sides, there's only one possible triangle to make. And that's why I can say one triangle is congruent to another one. So, because there is only one possible triangle with three given sides, they are the most stable shape. If I have these three lengths, this is the only possible triangle I can make. No matter how I arrange the pieces, it's just this triangle. Whether it's flipped, rotated, whatever it's been done, it's the same exact triangle. However, if I look here, this quadrilateral has the same lengths as this one over here. However, this is two different shapes. The one on the right is called a rectangle. The one on the left is called a parallelogram. But I use the same exact lengths to make both shapes. So, these shapes, stable. One possible combination. These shapes, not, because there's more than one. However, if I want to make something like a doorway stable, what I'll probably do is in the design of the building, I'll have it where there's diagonals being drawn. So that way, my shape becomes two triangles. This rectangle over here is now two triangles, and it's stable again. It won't move as long as it doesn't break. So, stable, it has to be made up of triangles. If it's not stable. So, are the shapes stable or not? It's what this question is really asking is the shape made up of only triangles? All right, and that's it for today. So what you need to be able to do is use a flow proof. Show triangles are congruent by side-side-side, whether you're doing a proof or whether you're just getting information to show that they're congruent, and be able to tell me if a shape is stable or not. If you got those three things, good. If you don't, double check. All right, till next time.